morning everyone. I'll be talking about understanding a pressure monitoring system. So what is a pressure monitoring system? It is a device which is used to monitor various pressures within the body. It could be arterial or venous, or it could also be intracranial pressure monitoring. So in this presentation, we'll be discussing about various parts of an arterial blood pressure monitoring system and also various physics behind the data which we get through these monitoring systems. So normally what we usually do is we monitor the arterial pressure of the patient, which consists of various parts of that monitoring system. Is an arterial catheter, which is usually inserted in the radial artery. Then there is a fluid-filled tubing, which is usually filled with saline. And this, with the help of various clamps and sapling cord, is connected to the pressure transducer system. So this pressure transducer system is the enlarged plastic structure, which is then fixed to a static pole or a place near which near the patient, which doesn't move a lot. Now this pressure transducer is then connected to a pressurized saline system, which consists of a normal saline which is wrapped in a pressurized bag, and it also has a wire which is connected to our monitoring device. So first, coming to the intra-arterial catheter, this catheter, it will provide us access to the arterial blood, and through this arterial blood we connect the fluid-filled transducer system. Now the characteristic of an ideal intra-arterial catheter is that it should be kink resistant, it should be made up of a biologically inert material, and it should be incompressible. Similarly, for the fluid-filled tubing, the tubing should be made up of a stiff, non-compliant material. It should be short and wide. Usually, the system which comes, it should have a fixed length, and much variations in the length should not be done. These fluid-filled tubing also has various sampling ports through which we can draw sample, and it also through these sampling port we can draw sample, we can also flush the system. And what this tubing does is it provides a continuity to the system. So now within the arterial catheter there is blood which is getting oscillated at a particular pressure. This is getting oscillated at a particular frequency depending upon the pressure system. Now once we connect the fluid filled tubing to the arterial catheter end, the pressure changes which is happening within the blood will get reflected to the saline in the tubing, and this saline will then communicate this pressure changes to the transducer, and it is at the transducer level where the data recording happens. So now the fluid in the tubing should also have certain characteristics. It should be incompressible. Normally, when the entire system is being manufactured, the entire calibration happens with the help of normal saline. So ideal fluid to be used in these systems should be normal saline. And it should always be under a particular pressure. So what we do is we connect one end of the transducer system to the saline bag, and this saline is then wrapped in a pressurized bag, and this pressure is the pressurized bag is inflated to a level of around 300 mmHg. Now what happens when you pressurize it to this high level? First thing is it prevents any backflow of arterial blood into the system. So this prevents this helps in contamination or prevents in formation of any clot within the system. Also, when the system is pressurized to such a high level, the normal saline is flows at a rate of 3 ml per hour into the system, and the catheter also doesn't block. Apart from that, there is also a small rubber kind of extension present at the transducer, which when pulled will allow fast flushing of the system. So when we pull this rubber tubing, the normal saline, it will flow at a rate of 30 to 60 ml per minute. This helps in keeping the system clean, keeping the system free of any blood residue, and also helps in performing the fast flush test which we have to perform after setting up of this system. Now coming to the pressure transducer. Now pressure transducer is the device where this recording of the pressure happens. So whatever oscillation or pressure changes which is happening in the blood, then in the saline, this gets transmitted to this transducer. Now transducer has a silicon diaphragm. So at this diaphragm level, the kinetic energy which is present in the saline will get converted to electrical energy. And subsequently, this electrical energy goes to the anesthesia monitoring device where the processing happens and we then get a digital data out of it. So this happens, this conversion from kinetic energy to electrical energy happens with the help of this silicon diaphragm, which is then connected to a Wheatstone bridge. We'll come to the principle and we'll discuss about Wheatstone bridge later. Now, once electrical energy is being made, we get electrical energy. This data goes to the anesthesia monitoring system where the signal gets processed, it is being analyzed, and then it's converted into a form where we can read it. So it gets converted into wave and it also gives us various values. And this data is then stored. So these are the various parts. So this is the arterial catheter. This is the three-way or the sampling port. Then these are the tubing which is filled with saline. This is then connected to another sampling port, and this is the place where the transducer system resides. The transducer, which is a diaphragm and a Wheatstone bridge. This then has two inlets. One is for the saline filled tubing, and one is the wire which goes to the monitoring system. As said, as I told earlier, a transducer is a device which will convert energy from one form to another. In our case, the kinetic energy gets converted into electrical energy with the help of a Wheatstone bridge. So now coming to a little bit more detailed discussion about pressure transducer. So this is the saline filled tubing, and this is in continuity to the silicon diaphragm. Now the characteristic of the silicon diaphragm is that as it moves, the shape changes, so it gets deformed. And with changes of the shape, the resistance offered by the silicon diaphragm also changes. So there is saline. This saline is in continuity to the blood. The blood is oscillating. There is some pressure which is being generated. This pressure gets transmitted to this saline, which also then oscillates at a similar frequency and it offers the same pressure. This pressure is then transmitted to this diaphragm, which moves. Depending if the pressure is high, it will move more. If the pressure is low, it will move less. This movement in this diaphragm will cause deformity. This deformity causes further changes in the resistance. And this resistance is what is being used. This change in resistance is what is being used to calculate the pressure. So this is a Wheatstone bridge. So what is a Wheatstone bridge? It is a system where there are 4 resistors. Ideally, these 4 resistors are in balance to one another. So the ratio between R1 to R2 is equal to R3 to Rx. Now Rx is the place where our diaphragm is situated. And this is variable. We don't know what resistance it is offering. We have to calculate that. But in our transducer system, we know the resistance of R1 and we know the resistance of R3. And R2 is the resistance which can be varied. So depending upon how the system is being manufactured, R2 is a variable resistance. So R1 by R2 is equal to R3 by Rx. Ideally, we want the system to have no current. When it is equivalent, R1 by R2 is equal to R3 by Rx, there will be no current flowing. But then there is changes in the blood pressure and so the Rx changes. Now once this Rx value changes, there will be a disbalance between R1, R2, R3, R4. The both sides will be not in balance. As a result, there will be some flow of current. The system of Wheatstone is designed in such a way that once the current is flowing, this R2 value will be adjusted. It will either increase or decrease with an intention to bring the current flow in this system to 0. So suppose Rx has increased. So what will happen? There will be some flow of current. Then what the system will do is it will simultaneously increase the value of R2 as well. It will simultaneously adjust the value of R2 so that ultimately the ratio is balanced and there is no flow of current. This value of R2, which is changed by the system, is definite. So the system is aware of what value R2 or what value we are adjusting R2 to. So once we know the value of R2, which brings the current in this system to 0, with the help of that R1 to R2 is equal to R3 to Rx, we can calculate Rx. And once we know the Rx, with the help of various algorithms and charts which have been plotted on the basis of studies done on healthy individuals, we can predict the value of the pressure offered. So this is the basic principle as to how this pressure calculation happens within the transducer. But now coming to setting up of transducer. So now any pressure which is being monitored or calculated in human body is over and above the atmospheric pressure. So if you are living at sea level, there is some amount of atmospheric pressure, and whatever body pressure we calculate, 100 by 70, that is above the atmospheric pressure. If you are living at 100 meters above sea level, there will be some amount of atmospheric pressure, and whatever BP is we calculated, that is over and above. So when a transducer is being manufactured, it doesn't know what is the atmospheric pressure. So once we set up the system, it is our work to make the transducer understand what is atmospheric pressure. So we have decided to set up the monitor. We have secured the arterial line. We have pressurized we have put a saline bottle. We have pressurized the system. We have connected the transducer system to it. The entire line is filled with saline, no bubbles, and we have connected it to the arterial line. Then what we have to do is we have to open the three-way present near the transducer to air. So that is known as opening to air. What happens is when we open it to air, saline from the pressurized saline bag will flow through the transducer to the port which is open to air, and then an air fluid interface will be formed. At this air fluid interface, the pressure being offered by the atmosphere is equivalent to atmospheric pressure. And once this is opened, when we press the button 0, set 0 or do zeroing of the device will calculate the atmospheric pressure and take it as 0. So this is known as zeroing the transducer. So making the transducer understand what is atmospheric pressure is known as zeroing. Then comes leveling. So now various pressures which we monitor, whether arterial, venous or intracranial pressure. This is being monitored with respect to a particular axis. So when we are monitoring any blood pressure, which is arterial or venous, we are interested in the pressure which is at the level of root of aorta, which is known as the phlebostatic axis. So now we know that whatever pressure is being calculated is calculated at the level of transducer. It is not calculated at the level of where arterial line is inserted. So our responsibility is to to place the transducer to such a level that the desired reading is being recorded. So we want it to be at the level of phlebostatic axis. So we want to keep the transducer at the level of root of aorta. So normally it is at the level of 4th intercostal 5 cm below the sternum. This is where the root of aorta will be lying. So this is the place where we want to keep it, and this is how we do the leveling. We see that how the posture of the patient is, whether head elevation or supine. Then we see where is the 4th intercostal space, where is 5 cm below the sternum. And then we draw a parallel line. We draw a line parallel to the ground from this line. And then at a pole nearby, we will fix the transducer. This is known as leveling. Now we have to understand that because the pressure is measured at the transducer level, if the position of the patient changes, if the patient is lying supine, we have kept it at a particular level. But suppose if the patient is standing, the phlebostatic axis will go high. And so we have to change the transducer level. Otherwise, the reading will be false high or false low depending upon how the position of the patient is changing. Similarly, when we calculate the intracranial pressure. So when we calculate the intracranial pressure, we want the pressure to be recorded at the level of external auditory meatus. So now external auditory meatus will correspond to foramen Monro. Foramen Monro is the part of the ventricular system. So we want it to be at that level. Hence, we will raise the transducer to that level. It raise the transducer to external auditory meatus level. Okay, so this is the table. So as said, various blood pressure system, our site of leveling is phlebostatic axis, and for intracranial pressure, our site of leveling is external auditory meatus. Now, once you have set, you have done the zeroing, you have done the leveling. Now, then you have to know whether your system is optimally performing or not. So, to know whether the recording which you are getting is reliable or not, whether the readings are correct or not, we have to understand two factors. One is natural frequency and damping coefficient. Now, natural frequency is like, for example, a pendulum. When you push the pendulum, it will start vibrating at a particular frequency. If you give a harder push, even then it will vibrate at the same frequency, but the amplitude will be higher. So, this inherent ability of a material to vibrate or oscillate at a given frequency, at an inbuilt frequency, is known as natural frequency. Now, what happens is blood is vibrating. It gets transmitted to saline. The saline is vibrating. Then it gets transmitted to the silicon diaphragm. Now, the silicon diaphragm is vibrating. So, now this diaphragm has a natural frequency. Blood is having a frequency at which it is vibrating. Now, our intention is that when the silicon diaphragm vibrates, it should vibrate at an inherently higher natural frequency. This would help in better recording and getting even minute details of the blood pressure system. So ideally what is being said is that for an intra-arterial blood pressure monitoring device, its natural frequency should be 8 times higher than the pulse rate. So normally in a human, how much is the maximum heart rate we want? Like in a normal sinus rhythm, it is like expected to be around 180 maximum. So the natural frequency of the arterial blood pressure transducing system should be 180 into 8 by 60, which is roughly 24 Hertz. So we want the natural frequency of our system to be around 24 Hertz. Now this natural frequency can be increased or decreased by various factors. So because to this transducer we have attached a cannula, we have attached a tubing, then there is a fluid in the tubing, there is certain diaphragm and the material of the tubing. All these factors can affect the natural frequency. So if you want to increase the natural frequency, what we can do is we can reduce the length of the cannula, we can reduce the compliance of the, we can use a material of the tubing which is not very compliant. Then the density of the fluid used can be decreased and we can increase the diameter of the cannula. All these things will increase the natural frequency. However, it is advised not to alter all these things. Usually, what has been said is that for a patient, a freshly manufactured transducer system should be used. But owing to various constraints, logistic issues, monetary issues, sometimes we do reuse our transducer system after proper sterilization. So in those cases, when we are using a sterilized system, we have to be cautious that because it has been sterilized, the material might have changed, the density, the length, the diameter might have changed. In those cases, our natural frequency would not be what is being proposed by the manufacturer. It would have changed, and then our readings might also not be proper. So in such cases, what we can do is we can measure the natural frequency. So how can we measure the natural frequency of the transducer? It is paper speed divided by wavelength. Normally, the speed which we keep on the monitor is around 25 millimeter per second. So what is wavelength? Wavelength is the distance between two wave crests. So a wave has a crest, this is the crest, and this is the trough. The distance between two wave crests is the wavelength. So paper speed divided by wavelength. So here in this example, the wavelength is roughly 1 millimeter. We can also calculate it on our monitoring device. So paper speed divided by wavelength 20. So here the paper speed is 25, wavelength is 1. So the frequency comes to be around 25 Hz, which is okay. We want it to be around 24. So here we are happy with the natural frequency. Now there is another component, a component which is known to give maximum errors during our recording. This is the damping coefficient. So what is damping? Damping is a situation where whenever a system is oscillating, after a certain time the oscillation will go on reducing till it stops. So damping is that factor which reduces the energy in the oscillating system. Every material, every system has its inherent damping ability, and this is known as critical damping. Now, once this damping is very excessive, so you can take damping as a kind of friction. So when the friction is very high, what will happen? The system will not oscillate, readings will not be proper. This is known as over damping. If damping is low, so suppose the system is very compliant, the material is very like flimsy, there will be no damping at all. There will be no friction offered. As a result, whatever resonance or oscillation is happening, it will be too varied, too high. So that is under damping. So friction is very less. This is under damping. And this damping is what we usually see is the most common source of error in our day-to-day practice. Now, damping coefficient is a number by which we can calculate how much dampness is offered by the transducer system. The damping coefficient value will be around 0 to 1. So what does 1 mean? So if our damping coefficient is around 1, it means that this very high. So system is not oscillating at all. No matter how much oscillation you give, how much pressure you give, the system won't oscillate. If it doesn't oscillate, you'll not get proper waveform. You'll get these kind of waveform where you're not able to appreciate the systole, you're not able to appreciate the diastole. So this is a kind of overdamped waveform. So overdamped waveform problems are systolic pressure reading will be low, diastolic will be unnecessarily high, and the damping coefficient will be around 1. However, even in this situation, the mean arterial pressure recording will be correct. Similarly, coming to the second waveform, which is this. What you see, we're seeing systole to be very high. There are too many waveforms and peaks in between, and then there is a diastole. So this is an example, a classical example of an underdamped waveform. Here there is a systolic overshoot, overread, and there is a diastolic underread. What is happening here is friction offered is very less. The dampness is very less. As a result, system is oscillating too much, and hence we are not getting an actual or an ideal waveform. Here, so the damping coefficient here will be very less. It will be around 0, or it will be less than 0.5. Now then, coming to the third waveform. This third waveform is the ideal waveform which we want. We want a systole, we want a diastolic notch and a diastolic pressure. So this is an optimal waveform. Here the damping coefficient is around 0.7, and when we get such waveform, we can rely on the systole or the diastolic pressure readings. In all these three, overdamped, underdamped and optimally damped waveforms, the mean arterial pressures are usually reliable. Systolic and diastolic is dependent upon what is the damping status of the transducer, but mean arterial pressure or the MAP is reliable in all the three cases. Now coming to how do we calculate the damping coefficient. So how we calculate? We can do a fast flush sign. So you have set up the system, leveling is done, zeroing is done, leveling is done. Then you pull the rubber tubing and then a fast flush happens and a square waveform is seen. After you release the rubber tubing, the system will oscillate and these oscillations gets recorded on our monitor screen. Okay, so you'll see few oscillations after which a proper arterial waveform will be seen. So these 2 or 3 oscillations is through which you can calculate your natural frequency and damping coefficient. Damping coefficient is the ratio of the amplitude of second waveform by amplitude of first waveform. So A2 is the amplitude of second waveform, A1 is the amplitude of first waveform. So A2 by A1. So how much will be the A2 here? It is like 1, 2, 2.5. So let it 2.5 is the amplitude. A2 is 2.5, A1 is like 1, 2, 3, 4, 5, 6, 7, 8. So it is 8. So 2.5 by 8. Roughly it comes to be around like 2.5 by 8 will be roughly around 0.3, 0.35. So your amplitude is somewhere around 0.4 to 0.3. And this means your damping coefficient will be between 0.28 to 0.36. So on an average, let it be 0.3. So how much do we want our damping coefficient to be around? We want it to be around 0.7. So what does this do? That your system is underdamped. Okay, so now once you know that the system is underdamped, what can be done to prevent or to optimize? You can optimize the position. The arterial line, sometimes it gets stained, maybe a clot is there, you have to flush, there may be saline bubbles, you have to flush that, and then you can see whether your system is getting optimized or not. So these are the basics of how to set up and how to optimize your pressure transducer system. This is valid for almost every pressure transducer system, be it arterial, be it venous, or be it intracranial pressure monitoring. Okay, so in conclusion, setting up of monitoring system is the first step to getting the right pressures. All the component of pressure monitoring system have to be in sync to produce the right reading. Leveling and zeroing are the most important steps while setting up of a pressure monitoring system. Thank you.